So in the last video, we started to cover parameterization a little bit more, and specifically these things called parametric surfaces. And parametric surfaces was basically just our way of kind of getting our feet under us in terms of, how do you describe the shape of an object when all you want is not the contents. You don't want what's on the inside of that object or the region trapped between two objects. All you want is the surface of that object. And so, for example, maybe just as kind of a reminder, we saw that if, say, you wanted to parameterize the surface of a cone, right? This right here is the top half of a cone. There's a couple ways you could do this. So version 1 might be to just keep it simple. So you can come up with a parameterization in terms of x and y. And this is the most basic parameterization. You just let x be x, you let y be y, and then you simply just restrict z to be 2 square root x squared plus y squared. And we talked about the pros and cons of doing this this way as well. And we could also use the fact that we know that, since we're using a cone and a cone is shaped like this, it consists of a bunch of circles, and that we might try using cylindrical coordinates or polar coordinates, and we might come up with a different parameterization in terms of r and theta, and maybe it's best to let x equal r cosine theta, and to let y equal r sine theta. And if we do this, or if we choose this parameterization, then what does z equal? Well, z is going to just equal 2r. And this right here is another parameterization of the surface of a cone. And which one do you pick? It's going to kind of depend on your application. So that was all the stuff that was entirely covered in the last video. And so now we're going to move on to actually using this stuff, which is completing a surface integral. So I want to remind you all, we talked about it in the last video, but a surface integral is talking about simply evaluating the points of the function along just the edge of this surface. So we're no longer talking about creating a 3D shape. We're not doing that anymore. We're not doing the intersection of that and some other function and finding the volume in between. We're not doing any of that anymore. We just want the values of the function on the surface of the object. And so in order to do that, we're going to need to recall something that we did earlier in the course. And we're going to need to recall an equation. And the equation that we're going to need to recall is the surface area of a function, right? Surface area of an object. Okay. And there's a really nice formula for this. We have seen this already. We did do this before, so I'm just going to kind of write it down, and then I will very quickly kind of re-explain where this comes from. So we have the magnitude of r sub u cross r sub v dA, and this right here is the surface area of an object. And if you don't really remember this, the general idea was, if you have, say, some 3D shape. Okay, so this is going to be a 3D sphere, right? And if you parameterize it, if we come up with a parameterization for this sphere in terms of two variables u and v, then at any point on the surface, we can come up with a tangent vector r sub u, which is with the partial with respect to u. We can come up with another tangent vector r sub v. And on a microscopic scale, if I tone those drawings back just a little bit, right? Maybe I'll move my point to be a little more here. So if we tone those back just a bit and we talk about that, there's my r sub u, and here is my r sub v, then we can approximate the area of this part of our object, right? Just this part right here, by using the magnitude of the cross product. So the magnitude of the cross product of those two vectors, those two tangent vectors, gives us the area of this parallelogram, which on a microscopic scale is roughly exactly the area of the surface of this object. And so what we're doing is basically we're this right here is our surface area approximation. Surface area approximation. And where does the dA come from? This kind of comes from telling us, over what region of U and V values. Okay, that's what we've done before. And an alternate version of this was, if we didn't parameterize things and if our shape was just in terms of, say, x and y, right? If we have our function, our surface in terms of x and y, then the surface area formula looked very similar, but we got the square root of I'll put df dx squared plus df dy squared plus 1 dA. Okay, so these were our two formulas that we have used before for surface area. And so if you would like to review these, you can go back in the section we covered on surface area before, which let me check back in the book. Chapter 15.5. So this is chapter 15.5 in the textbook. So if you're looking for it in the YouTube videos, it is after double integrals and before triple integrals. But we're going to need this to help us actually compute surface integrals. Once we kind of understand that and we feel comfortable with the fact that this magnitude of RU cross R sub V is basically an approximation of our surface area, we can start to kind of hopefully reason at this point how a mathematician might assume, how do you calculate the value of a function on just the surface of an object, right? So if I have f of x comma y and I want to evaluate the value of my function on the surface of this, say, sphere, you can imagine, just like we did with double integrals in the past, that we're going to use a double integral over some region of integration, and we're going to add up the values of the function, f of x, y, over basically the surface area of our shape. That's the idea. So before, when we were adding up for, say, line integrals, a line integral, maybe I'll do this off to the side. A line integral, we had some path and we said, here's the value of our function f of x. And so we were adding up the values of our function over some bit of the path, right? A really, really tiny bit. And for us, if we were in terms of x and y, this became our ds. And so when we upgrade this to a surface area integral, a surface integral, we are basically evaluating the value of our function over some bit of the surface of our object. So maybe I'll write that instead. So this second bit right here is some bit of our surface. And hopefully that should make sense. Not be too bad, and we can basically fill in this blank and say, well, that, after seeing what a surface area calculation is, a little bit of our surface is just magnitude, RU cross RV if we parameterize things, dA, or it's going to be the square root of, df dx squared plus df dy squared plus 1 dA. And so either one of those things is going to go here, and it depends on if we decide to swap out x and y and parameterize those in terms of u and v, or are we keeping everything in terms of x and y? So let's see if we can kind of do an example to kind of drive this home. So let's see. For example, do I have one prepared? Nope, I don't. But let's do one anyways. Surface. Example. Oh, this one won't be too bad. Okay, so for example, let's evaluate this function, just f of x is equal to y, okay? Very simple, not too bad, over some surface. So this is the new notation that we're going to see. So this right here is our surface S, and this right here being our small, change in our surface, which is essentially the stuff that I just pointed out before. So let's evaluate this surface integral. And we're going to say, let's let S be the surface. Let's define it to be the surface where z is equal to x plus y squared, where 0 less than or equal to x less than or equal to 1, and 0 less than or equal to y less than or equal to 2. Okay, so let's go ahead and do this. So hopefully right off the rip, we can see that we have a relatively nice surface that we are integrating over. Okay, this isn't so bad. It's parabolic in one direction. It's a plane in the other direction. So I think it probably looks something kind of like this, right, where it kind of arcs up a little bit. And we're just trying to add up the values of this function over the surface of this particular shape. And we've been given the restrictions, that we're simply talking about the chunk of it that lies where x goes from 0 to 1 and y goes from 0 to 2. So we're trying to do it for the chunk of this shape that lies over that region. So maybe that's this piece, and obviously the shape probably kind of continues like this, right? So we're probably just talking about the chunk of the region, the chunk of this shape that's kind of like maybe here or something. This is the part of our orange surface that we want to evaluate the value of this function y over, okay? So here we have a nice surface. We don't really need to parameterize anything because we don't have anything that indicates in our surface that we should use polar coordinates or cylindrical coordinates or anything super fancy. So my first attempt is simply going to be that to evaluate this surface integral, it's going to be a double integral. It's going to be over those x and y bounds. So I'm just going to put my x bound from 0 to 1 and my y bound, say, from 0 to 2. And then we will have our function, which is y. And now what about this ds? What do we do with this ds? Well, remember, this is over our small change in the surface, right? We need our chunk of surface. And our chunk of surface, we saw, came from that equation magnitude of RU cross RV, or it comes from the square root of the df dz squared, etc. And so we're going to use the square root version because we have everything in terms of x and y. We don't need to do anything else. So according to this formula up here, what we need is our partial with respect to x, which appears to be 1. So this is going to be 1 squared. Then we need the partial with respect to y. That's going to be 2y quantity squared. So that's going to be, I'll just write here, 2y quantity squared. And then plus 1. And then we have a dA on the outside. So again, this all comes just from the surface integral formula that we came up with before. The stuff in white is basically our small surface area. Y is going to be our function. And so this double integral we get set up as 0 to 1, 0 to 2, y times the square root of, let's see, 4y squared plus 2 dy dx is how I have it set up. And I'm not going to go ahead and solve this because this is just calculus 2. This is a u substitution. This will not take too much effort, and we will hopefully get some answer, which I believe is supposed to be 13 root 2 over 3. Awesome. Okay, so that's an example of doing a surface integral. You're going to use the other equation if, let's say, we were doing if we were doing a surface integral over, say, a cylinder or something that we needed to parameterize the other way. Okay, maybe should I do one of those? Yeah, I'll just do the next example in the book. So we'll do one more example, and then we'll take a small break and separate this into 2 videos. So let's do one more example. So evaluate. All right, let's evaluate the surface integral of the function, a very simple function, just z ds. And we're going to say, where S is, it's going to be a surface that consists of multiple sides. So S is a surface with 3 sides, okay, 3 sides. And I'm going to separate them for us. So let's see. So S1 is given by the cylinder, x squared plus y squared is equal to 1. S2 is the bottom of this cylinder. It's the disk. It's going to be the disk, x squared plus y squared is less than or equal to 1 in the plane z is equal to 0. And let's say S3 is basically going to be a part that's going to cut off this cylinder at kind of like an angle. So let's say this is the plane z is equal to 1 plus x. Okay, so what does the shape look like? You are welcome to use GeoGebra or any graphing software as per usual. I will try and come up with just a very rough sketch of what this looks like. So we're going to have a cylinder, so that's given by S1, but it's cut off by some planes. So maybe I'll try and draw the cylinder first. Okay, so here's our cylinder. X squared plus y squared is equal to 1. Has a projection of the unit circle down onto the plane z equals 0. We're getting cut off by this plane z is equal to 1 plus x. So I'm just going to kind of create a plane that kind of does this. Right, something like this. It's getting cut off, and it is going to leave an intersection of something that kind of looks like this. Right, and then our S2 is going to be the bottom part of this surface. The S2 is kind of down there. It's the bottom. It's that circular bit. So maybe I can erase some of this to try and help clarify part of what this shape looks like. So maybe we'll erase this part, and because this is the part that's not really under it. Okay, so we have this, and we're interested in the surface of the shape that is given by this intersection of the plane. That right there is going to be our S3. That's our plane. The bottom part, which is the circle, that's our S2. And the side of this shape, which is the cylinder, is going to be S1. So we have 3 completely different surfaces here, which means we're going to need to do 3 completely different surface integrals. So we can kind of start wherever we want. Let's see, where might we start? Well, I guess we could start with S3. That's pretty much the easiest one. Why don't we start with S3? So S3, right? Not S3, sorry, the S2. S2 is just the bottom of this thing. So S2 is pretty easy. So it's kind of just like a circular surface. And it's given by x squared plus y squared. It's basically everything that is on the contents of that circle. So how do we go about doing this? Well, this part of our surface integral is actually going to be the easiest, because on this entire shape, what property does this have? This is on the plane z is equal to 0, and we're doing a surface integral of our function, which is z ds. And since S2 lies on the plane z equals 0, we're just going to, no matter what we put in for ds and when we parameterize this, our z is going to equal 0. So this right here is just going to evaluate to 0. So S2, if we add up the values along S2, we're just going to get a value of 0, which should make sense, because if we're adding up all the z values, what are all the z values along S2? Well, all the z values are equal to 0. So could draw a line in that. Cool. So now let's go ahead and move on to the more interesting ones. Let's see here. So S1, let's tackle S1. So this first surface. So S1 is described by a couple of things. It's described by x squared plus y squared is equal to 1. That's the outline of the circle. But our z value has the property that z, right, like where do we cap this cylinder at? It's trapped underneath the plane 1 plus x, and above the line z is equal to 0. But we can still parameterize this surface pretty easily, because we can recognize this is a cylinder, so we're probably going to stick, and it's a cylinder of radius 1, so we could create the parameterization in terms of, say, theta and z. And you might be like, Dylan, why don't you have an r there? Well, because we're dealing with a cylinder of radius 1. So our x is going to equal not r cosine theta, it's just going to equal cosine theta. Our y is going to equal sine theta. And we're just going to let z be equal to z. That right there is a good parameterization of our cylinder. And we impose the restrictions that theta goes from 0 to 2 pi. And we impose the restriction that z goes from 0 to, well, it was 1 plus x, but we replaced x with cosine theta. And so this right here, in its entirety, parameterizes the wall of the surface of this cylinder. So it's covering the wall of the surface of this thing. And I don't know how to do it except for highlighting it a little bit, but we're just talking about the wall of S1. That is what we're handling right here. So that we don't get lost, right? Remember, we're trying to evaluate this surface integral over all of S, and S consists of 3 pieces, right? It's this, all 3 sides of this object. And right now what we're doing is we're doing the surface integral over S1 of the function z dot ds. And so now we're going to try to evolve this integral. And so hopefully we remember from our formula that we'll have z, but what does ds become? Well, our small change in surface is, r sub u cross r sub v dot dA. And in this case, our u here is going to be theta, and our v here is going to be z, because those are the parameters that we chose to describe this cylinder with. And then so that means that our dA is going to be in terms of d theta dz, or dz d theta. All right, so let's go ahead and do this really quick. So if we calculate, the first thing we need to do is we need to figure out what is r sub theta. Well, that's not too bad. R sub theta, that's just going to be negative sine theta cosine theta comma 0. And then our r sub z, that's going to be 0, 0, 1, hallelujah. So when we do the cross product of this, we're going to get our I, our j, our k. And we do the cross product of these two things, we'll pop them in, negative sine theta cosine theta 0, then 0, 0, 1. And if we do this, everything is going to pretty much just cancel out. So in our first one, we should just be left with cosine of theta. So in the I direction. In the J direction, we're going to be left with sine theta. And I believe in the K direction, we're just going to get 0. And so now all that's left to do is to get the magnitude of this. But the magnitude of this is, so we want, remember, this is the magnitude of the cross product is what we want. And so that's going to be the square root of the first term squared plus the second term squared, which is going to be sine squared plus cosine squared, which is just 1. So this is 1. Holy smokes, this works out to be really nice. So kind of just recapping what we've done before, we're basically working on this surface integral right here. We just figured out this chunk right here evaluates to be really nice. That's just 1. Z is already in terms of Z because that's one of our parameters. And so now we can just set up this double integral to be the double integral of, we'll let theta go from 0 to 2 pi. Our Z needs to be the first one because it goes from 0 to 1 plus cosine theta. And then we're just going to have our Z times dz d theta. And so this, again, I'm going to stop here. It's worked out in the textbook if you'd like to do it. But this is going to, after a little bit of work, equal 3 pi over 2. And so this is the parameterization of S1, and then this is doing the surface integral over S1. We already did S2, and then S3 isn't going to be so bad either. It's just a plane. And so if we kind of finish this off by taking care of S3, so we're going to do the surface integral over S3 of z dot ds. S3 is just a plane 1, z is equal to 1 plus x, and so we can replace this with 1 plus x. What are we going to do with ds? Well, again, we don't really need to parameterize the plane 1 plus x in the slightest, right? So we can just go ahead and use the part of the formula that says ds is going to be the square root of df dx squared plus df dy squared plus 1, and then we can keep this in terms of dx dy or dy dx, kind of depending which one we're doing. So for us, this, because remember, this is the surface where z is equal to 1 plus x, df dx is just going to equal 1. df dy, that's just 0, and then we're left with a 1 here. So it looks like this isn't going to be too bad. We have a double integral, and z is equal to 1 plus x. And then we have the square root of 2 here, and then our dot dA, right? Dot our dA, which is of this form here. Now, the only problem is, what are our bounds? And so if we go back to our shape, we kind of notice that the bounds of this, the green part of this plane here, the bounds of this, the x and y bounds, lie perfectly over this circle here on the bottom, that our x and y bounds are circular in nature. And so again, polar coordinates probably going to come into effect here, and that is indeed exactly what we're going to use. So at this point, I'm simply just going to let x be equal to r cosine theta. I'm going to let y be equal to r sine theta. And you might be wondering, Dylan, how come you're letting x be equal to r cosine theta? Well, because in the shape, we want all of the points that are on this surface right here. And that includes every single point that is inside this kind of projection circle that is sitting on the ground right here. And that includes us using r cosine and r sine theta. But this isn't so bad. We're going to be done actually pretty quickly because since this is just a unit circle, we're going to just have theta goes from 0 to 2 pi. r goes from 0 to 1. Our function, which is z is equal to 1 plus x, now becomes 1 plus r cosine theta. We have our square root of 2 that we came up with earlier, and then our dA becomes r dr d theta. And again, from here, you can go ahead and finish solving. It's going to end up being the square root of 2 times pi if you actually do this. So what this means is that in totality, the surface area, or the surface integral of this entire shape of the function z, right, over the surface, is just going to be all of our results. So it's going to be the results from S1, which is 3 pi over 2. It's going to be the result from S2, which is 0. And then the result from S3, which is square root 2 times pi. And so that is going to end up being our very fun answer. Awesome. Okay, so, just so we're not getting lost, remember we're adding up, why are we doing this? We're adding up all the values of a function over the surface of our object, because a lot of times we're interested in the electrical charge of something. Are we going to get shocked? Will we be able to conduct electricity? Is the surface of an object hot? Is it cold? Just a whole bunch of is the surface tactile or not? Is there going to be a lot of friction? Am I going to stick to it? Am I not going to? Right? A lot of times we actually don't really care what's going on the inside. We care what's happening at the boundary. And so that's what doing these surface integrals is pretty much all about. So hopefully that wasn't too much for you to kind of bite off and digest. And if it's not, go ahead and head on over to the next one.